Okay. We'll wait for the recording to start. Okay. So good evening. Time really passed. I mean, for me, I also hope that time really passed for you all. So this is our week. This is Mechange 3A, and this is our week 11. Okay. So I'll talk to you about our agenda first. So we're going to continue a topic that we started last week, right? And I'm going to continue. So this is the principal stresses. We'll go look at principal stresses in beams under combined loading. And then after this, we're going to do with 3D Mohr circle. Okay. Then our final exam. Our final exam will be held on August the 3rd. And it's going to start at 7 p.m. and it's going to go up to what was the amount of time I gave you for your term test? Can you remember?
It went up until 11.
Okay, so the same. So until 11 p.m. Okay, the same thing. Okay, I will talk to you about how many questions later on. Okay, probably next week. Okay, so just to make sure that yeah, make sure you have nothing on August the 3rd. I think August the 3rd is on a Tuesday. Okay, if anyone. And it's going to be online. Okay, open book or whatever. Okay, right. So that's what. So if we go into where we finished off last week, right? So last week lecture, okay, last week lecture, we talked about this problem, okay, which I'm going to continue. So this is a beam, and as you can see, this is by the way, this is last week's notes, okay? So if you were to refer to last week notes, okay? So we are going to this is the load that that the overhanging beam has been is carrying, right? So point A to point C is the evenly distributed load, okay? Point A to B is overhanging, B to D they're supported. At point B, we have a support of a pin, and point D has a roller, right? So last week we spoke about the distribution, right? So this over here is the distribution profile which we drew, right? So now this distribution profile, we focus on this section over here. Okay, we focus on this section over here, and we realize that we have high bending moment at this point. Okay, and we also have normal stresses. What we realize is at the neutral axis, our normal stress due to bending is 0. As you can see over there, I just had, whereas the maximum shearing stress is at this position over here. So the question asks, then how do we calculate, or where do we calculate to see our structure can withstand the load? So where the structure is going to fail, the structure is also going to fail where I'm circled in blue now. You can see that, right? That is the location where the failure. So highlight over again, failure will occur at the junction of the flange and the what? And the web. Okay. So I'm not going to teach you about fillet radius. Okay, this class is not about fillet radiuses. This class is about normal stresses distribution. Okay, and not consider the fact of stress concentration. Whereas when you go to 3E, then we go into stress concentration factor. So i.e., we are only interested in the stress distribution in the entire structure, or with beam critical, which is at the location of the flange and the web. This is the region where it's going to fail. We will not be focusing on what fillet radius we put on. Okay, that is the next course that you're going to take. Okay, so what I'm going to do, I'm going to take this entire page. Okay, I'm going to copy, and I'm going to put over here. Okay, so I'm going to get this entire thing across. Give me a moment. Okay. So now we're going to solve the beam issue now. Okay, we want to, so the purpose of this, or what will we ask in this question, is we were to ask to find the maximum. Okay, we asked to find the maximum principal stresses acting on the beam. Okay, so for this problem, the beam is selected as W250 by 28.4 millimeters wide. Okay, so last week we also, so just to recap, so the first thing to take note, right? The first thing to take note is we follow the transformation of the of the handbook. Okay, so X is that direction, Y is that direction. So we impose this into our problem over here. So we drew this transformation. Okay, so from here we know that what we are given, we have selected 28.4. So this is the entire W250 28.4. So what we are given is what we know is the maximum, or for this problem, okay, which is given the maximum allowable normal stress, normal stress, the stress allowable is equal to 160 times 10 to the power 6 Pascal. Okay, so from the data handbook, we find our IXX. Okay, we take our IXX value, which is equal to 40.1. Change everything to meters at this stage. Okay, right? Then now one thing I want you to highlight is we are going to look at this this particular term over here, which is SX. Okay, this particular term. Okay, so we write down first. So XX is equal to 308 times 10 to, hold on, I can't see, times 10 to 10 power 3, sorry, millimeter cube, or it is 308 times 10 to power minus 6 meter cube. Okay, so we are given it. Now, why I'm concentrate on XX, because our normal stress is bending about the x-axis. Okay, so now how is this related? So what is SX? Okay, so the thing is, what is this SX? Okay, so it is basically it's a function. Oh, sorry, it's a constant, not a function. Okay, so when you calculate the normal stress, okay, so not normal stress, the maximum normal stress due to bending moment, right? You have stress max is equal to so for this case we have mx over ixx multiplied by y. Okay, then we are going to let s or let xx is sx, okay, is equal to ixx over y. Okay, so therefore once we have got that down, so therefore we can also write stress max is equal to mx over sx. Okay, so let's look at example, is that true? So let's calculate it. So sx, so we know that sx, so we know that ixx, okay, look from the table, ixx is 40.1 times 10 to the power minus 6. The y, okay, which is the maximum distance from the centroid, which is d divided by 2, is 0.259 divided by 2. Okay, so 0.259. So when we calculate this, so this is equal to 40.1 power minus 6 divided by 0.259 times 2. So it's equal to 309.653 times, should move this further, sorry, right, times 10 to the power minus 6 meter cube. Okay, so this value, so what they do in the handbook, they did rounding. Okay, so this value and this value are very similar. Okay, so that's how they calculate sx. Okay, sx. Okay, so probably you have seen this in 2P04 also. Okay, I did not use this when we're calculating stresses due to bending moment, but it's just a constant. The most important thing is the constant is equal to sx is equal to iyy, second moment of area, divided by the maximum distance from the centroid. Okay, so that clears that. Okay, so the next thing that we want to find out is this structure is under combined loading, right? We need to calculate now. For now, we don't know, right? We need to find out the normal the bending moment and the shear force in the entire structure. So we have to construct shear force diagram, okay, and bending moment diagram. I know you guys have done this before, okay, but I want you to see how we can construct this based on mathematical equation. Okay, so we are going to start with, we're going to form, here we're going to form the uh, shear force and bending moment equation. Okay, that's what we're going to do, right? So first thing of all we're going to do, right? Now this question is okay. What I'll do is I'll copy and paste so you can see clearer. Okay. Or not, you can't see. It gets back. Okay. So we're going to draw the free body diagram. So again, this is our y